Hello guys, welcome back to my channel. Today we are going to talk about the distributed training of a model with PyTorch. What do I mean? Well, imagine you have a model that is very big and you have a lot of data upon which you want to train this model, but it takes a lot of time to train it because maybe your GPU is not so powerful, or maybe you cannot use a large batch size, or just you have a lot of data to train this model and you want to train it in a reasonable time. One way to do it is to parallelize the training on using multiple GPUs or even multiple computers, each one having multiple GPUs or even one GPU. In this video, I will show you how this distributed training works, how to integrate it in your existing project, and we will combine theory with practice, which means that I will give you all the theory behind the distributed training and then also show you how to first of all build the cloud infrastructure to do cloud training of a model, and also how to integrate the distributed training into an existing model that you have already built and it's maybe already training on a single GPU. So let's review the topics of today. First of all, I will give you an introduction to distributed training and show you the two ways in which we can do it. One is data parallelism and one is model parallelism. In this video, I will explore data parallelism. We will see a little bit of the neural networks theory because I want to introduce a concept called the gradient accumulation, which is very important for distributed training. And later we will see distributed training as it is built in PyTorch, so distributed data parallel. We will see how it works, and I will also show you what we mean by communication primitives, because maybe you have heard terms like all reduce, broadcast, all gather, etc. But you maybe don't know what they are or how they work. In this video, I will show you the algorithms upon which these operations are built and how they work when we talk about distributed training. I will also show you how to manage failover of a node. So imagine you are training on multiple nodes and one of the nodes suddenly dies. How we manage this situation? We will do a little coding session. I will not write code. I will just take an existing code and show you how to add the distributed training to an existing model. And I will be using a model that I built in a previous video. So it's the video about how to code a transformer model from scratch. So if you have already watched my previous video on how to do it, it's wonderful. If you didn't, it's not a problem, because anyway, the knowledge I will give you today applies to any model that you have built, not only the one wrote by me. And I will also show you the underlying mechanism in which PyTorch does distributed training. So I will introduce you the computation-communication overlap and the bucketing, which are optimizations made in the PyTorch implementation of the distributed training. And so we will explore all these topics. Let's start our journey. So let's start by introducing what is distributed training. Imagine you want to train a language model on a very big data set, for example, the entire content of Wikipedia. Now, the data set is quite big because it's made up of millions of articles, and each article has maybe thousands of tokens. To train this model on a single GPU may be possible, but it poses some challenges. First of all, the model may not fit on a single GPU. This happens when the model has many parameters. This happens, for example, also with the latest Llama. They have billions of parameters, and with so many parameters, the RAM of the GPU may not be enough. Or you are forced to use a small batch size because a bigger batch size leads to the out of memory error on CUDA. Or the model may take years to train because the dataset is very big. If any of the above points applies to you, then you need to scale up your training setup. And scaling can be done vertically or horizontally. Let's compare the two options. Vertical scaling means that you have a single machine, for example, a single GPU, which has some RAM and the GPU has some memory, for example, 4 GB. Vertical scaling means that you just buy a bigger computer or a bigger GPU. So you take the existing machine and you upgrade the hardware. And this requires no code change because the code that was running on the small machine can also run on the big machine. You just maybe need to adjust a little bit of the parameters. Maybe you can increase the batch size now. With horizontal scaling, we go from a single machine to multiple machines, each one interconnected with each other that are communicating for this parallelization training. And each machine may have one or multiple GPUs. And this requires code change, but this code change is minimal thanks to PyTorch and its implementation of the distributed data parallel. And in this video, we will explore horizontal scaling. Because vertical scaling, basically, we don't need to do anything. There is no code change. So There are two ways of distributing training of a model. One is called the data parallelism and one is called the model parallelism. So if the model can fit within a single GPU, then we can distribute the training on multiple servers, each one having one or more GPUs, with each GPU processing a subset of the entire data in parallel and synchronizing the gradients during backpropagation. This technique is known as data parallelism. So we have one model that can fit within a single GPU, and we have a lot of data. What we do is basically we split this data into subsets and we train it on multiple computers in parallel, such that each GPU is training on a subset of this entire data set. If the model, however, cannot fit within a single GPU, then we need to break the model into smaller pieces, into smaller layers, and each GPU processes a part of the forward and the backward step during gradient descent. This option is known as model parallelism. So imagine this model, initial model, doesn't fit on a single GPU, so we can break it into layers, and each computer is managing a layer, not the entire model. And of course, we can also combine data parallelism with model parallelism to create a hybrid option. In this video, we will focus on data parallelism. So we pretend that we have a model that is complex, but it can fit on a single GPU, but we have a lot of training data, and it's taking really forever to train it on a single computer. So we want to distribute this training on multiple computers or multiple GPUs, such that each GPU will train on a subset of the data. Okay, we need to review a little bit of the neural networks because I need to introduce a concept called gradient accumulation. Okay, imagine you want to train a neural network to predict the price of a house given two variables, the number of bedrooms in the house, and we will call this variable x1, and the number of bathrooms in the house, and we will call this variable x2. We think, because of some intuition, that the relationship between the input and the output variable is linear. So we can write that the predicted price is equal to x1 multiplied by the first weight plus x2 multiplied by the second weight plus a bias term. Our goal is to use stochastic gradient descent to find the values of the parameters w1 and w2 and bias, such that the mean squared error loss between the actual house price and the predicted house price is minimized. In other words, we want to find the w1, w2 and the b such that we minimize this quantity here. How do we do training loop with PyTorch without gradient accumulation? So first of all, we run the training for a few epochs. We take our training data, which is made up of x1, x2, and the target price. We calculate the output of the model, which is basically ypred is equal to x1 multiplied by w1 plus x2 multiplied by w2 plus the bias. Then we calculate the loss. We do backward on the loss. This will calculate the gradient of the loss function with respect to each parameter. And then we update the parameters using the gradient we have calculated. I am not using the optimizer. I'm just writing the update rule by hand. So using a learning rate, I don't use the momentum just for simplicity. And this is actually how the training loop works, right? So this part here is equivalent to calling optimizer.step, and this part here is equivalent to calling optimizer.0. Let's see it graphically, what happens when we do a training loop like this. So imagine we have our expression which represents the model, which could, in this case it's a very simple expression, but imagine it's a very complex model, okay? What PyTorch will do, it will create a computation graph. So it will take our input, it will multiply it by the W parameters, each input with its own weight. Then it will combine the sum of the two plus the bias term. This will produce an output. Then we have a target. The target is compared with the output to produce a loss. And then we run backpropagation to calculate the gradient of the loss function with respect to the target. So let's visualize the training process one item at a time using our computation graph. Imagine we are training on the input x1 is equal to 6, x2 is equal to 2, and the target is 15. The first thing our model will do is will start from the two input nodes, so x1 and x2. It will multiply by the w weights. And we also think that the W weights have been initialized with the following values. So the value of this weight is 0.773, this weight is 0.321, and this weight is 0.067. These values could be randomly generated. as we usually do actually. PyTorch will produce the output of this node, which is multiplying the x1 value with w1. Then it will combine the two, producing the output of the model. It will compare it with the target to produce a loss, which is a number, but it's also a function, so we can calculate the gradient. So now usually we call a loss.backward to calculate the gradient of the loss function with respect to each parameter, so w1, w2, and b. PyTorch will also compute the intermediate nodes, but I will not show them here for simplicity. So we run loss.backward. What will loss.backward do? It will calculate the gradient of the loss function with respect to each weight. How does it do it? Well, the first thing it will calculate the gradient of the loss function with respect to the output, which can be done like this. Then it will calculate the gradient of the output with respect to this node. Here I am showing only the computation of the gradient of the loss function with respect to the W1 node. You can do the other ones for exercise, for example. So next it will compute the gradient of the loss function with respect to the Z1 node, but in order to do it, because of the chain rule, we need the gradient of the output with respect to the Z1 node. And then it will compute the gradient of the Z1 node with respect to W1, and this allows us to calculate the gradient of the loss function with respect to W1. These are all the calculations that you need to do in order to get the gradient of this node here. And as you can see, we also need to compute the gradient of the intermediate node, but we are only interested in order to arrive to the gradient of the parameters, of the loss function with respect to the parameters. And these are the values for the gradient that we have calculated for each parameter. The next thing we do during training is we run optimizer.step. This will update the value of each parameter using the gradient that we have calculated. And how do we do it? We do say that the new value of the parameter is equal to the old value of the parameter minus a learning rate multiplied by the gradient. Why minus? Because the gradient indicates the direction in which the function grows the most, but we want to move against this direction because we want to minimize the loss, so we put a minus sign here. And this is how the value will be updated using the gradient that we have calculated in the previous step, which was the loss.backward function. The next thing we do is we run optimizer.zero. So this will zero out all the gradients of each parameter and also the intermediate nodes. And then we do the next iteration on the next item. So imagine we are training one item at a time, so batch size is 1. The next item may have x1 is equal to 5, x2 is equal to 2, and the target may be 12. This will produce this loss and this output. The next thing we do is we run loss.backward. Loss.backward, we calculate the gradient of the loss function with respect to each weight, and you can see the gradient here. The next thing we do is we run optimizer.step, which will update the value of the parameter using the gradient that we calculated in the previous step and the learning rate. And finally, we run optimizer.zero, and this will reset all the gradient for all the weights. We may want to visualize this on this process on the loss function. So let's see what happens to the loss function while we are doing this process. We started with some initial weights. So remember, we started with some randomly initialized weights values. Then we ran forward step on the first data item. This calculated an output, and then we ran loss.backward. This resulted in a gradient being calculated for the loss function with respect to each weight. This indicates a direction in which we should move our weights in order to minimize the loss, because we move against the direction of the gradient. So the arrow is pointing already in the negative direction of the gradient. The next thing we do is we do optimizer.step. Optimizer.step will take our initial weights and will change the weights value according to the negative direction of the gradient. We then run optimizer.zero. This just resets the value of the gradient. And then we run forward on the next data item. Then we run loss.backward, and this will result in a calculation of a gradient, which indicates the direction in which we need to move our weights in order to minimize the loss function. And then we actually modify our weights using optimizer.step. So the actual update of the parameters values happens when we call optimizer.step. And finally, we run optimizer.zero. and this will reset the gradient to 0. And this is how gradient descent works without accumulation. And without gradient accumulation, at every step, so every data item, because here we pretend we have a batch size equal to 1, we update the parameters of the model at every step. And however, with gradient accumulation, we don't do at every step. Let's see how it works. So the initial part of the training loop with gradient accumulation is the same. So we have run for a few epochs. We extract the data from our training data. So x1, x2, and target. We calculated the loss just like before. We run loss.backward just like before. The difference is here that we don't update the value of our parameter at every item we train our model upon, or every batch we train our model upon, but we do it at every few items or every few batches. In this case, I do it in this training loop, we do it every 2 items because we are extracting 1 item at a time from our training data. And so we update the parameters using the gradient every 2 items in this case. And what happens is that when the first item, for example, we will arrive to loss.backward, we will not run this code here. We will restart the loop at the next item. We will calculate the output. We run again loss.backward, and this loss will produce this loss.backward will calculate a gradient. But this gradient will not replace the gradient that we calculated in the previous step, but it will be accumulated. It will summed up to the previous gradient. So let's visualize this process step by step. Imagine we have our first item, and this is x1 is equal to 6, x2 is equal to 2, and the target is 15. We run the forward loop using this item. This will result in an output being calculated, and using the target we can calculate a loss. We then run the loss.backward. This will result in a gradient being calculated for this item. Then we don't update the parameters, we do forward step on the next item. So note that during this forward step, the gradient is not 0 because we didn't zero it out in the previous step, because in the previous step we didn't run optimizer.step or optimizer.0. So the gradient is still there from the previous item. And okay, the second item, which is x1 is equal to 5, x2 is equal to 2, and the target is 12, will result in a loss being calculated and an output. We then run loss.backward, and the PyTorch will not replace this new gradient with the previous one. We'll sum it up. It will be accumulated. That's why we call it gradient accumulation. So the new gradient is accumulated with the old one. Now that we have reached the batch size, we can now finally call the optimizer.step method. This will result in the values of the parameter being updated using the cumulative gradient. And then we run optimizer.0, which will reset the gradient to 0, and then we can proceed with another loop of two items, etc. Let's visualize what happens to our loss function, so to our parameters and the loss function when we do gradient descent with gradient accumulation. So our initial weights are here because they are randomly initialized. We run the forward loop on the first item. This will result in an output being calculated by the model. Then we run loss.backward. This will result in the gradient being calculated with respect to the first data item. And this gradient will indicate the direction. Then we run again forward on the second data item. And then we run loss.backward in the second data item. This also will result in a gradient being calculated. But these two gradients will then be summed up by PyTorch, and this will result in a resulting vector that indicates a direction. And then we run the optimizer, so we do optimizer.step, which will update the values of our weights according to the direction indicated by the sum of the two gradients of the two previous data items. And then we run optimizer.0. This will result the gradients to 0 for all the nodes. And so with gradient accumulation, we update the parameters of the model only after we accumulated the gradient of a batch, and we can decide how much we want this batch to be. So gradient accumulation is used not only distributed training, it's also used, for example, when you want to accumulate the gradient without increasing the batch size, because maybe a bigger batch size doesn't fit in your GPU. So you can accumulate the gradient for more than one item and then move the parameters, because this will result in a more smooth training. The loss will oscillate less, for example. And now that we have seen how gradient accumulation works, let's see distributed data parallel training in detail. So how does it work, what we mean by communication primitives, and how do we manage the failover. Okay, distributed data parallel training. So imagine you have a training script that is running on a single computer, but it's very slow because the dataset is very big and you can't use a bigger batch size because it will result in an out-of-memory error on CUDA. Distributed data parallel is the solution in this case. It works in the following three scenarios. So imagine you have a model that can fit on a single GPU and you have a training loop that works, but it's very slow. So the first thing you can do is you want to train the model on multiple servers, each one having a single GPU, and this can be done with distributed data parallel. The second setup that you can use is you want to just increase the number of GPUs on your existing computer, and this one also can be managed by distributed data parallel training. The final setup that you may want is you want multiple computers and each one having more than one GPU. In this video, I will show you how to implement this setup here, because the other two setups are just a particular case of this one. So this is the most generic setup we can have. And I will show you, how to create the cloud infrastructure for this setup, and also how to convert an existing code into distributed training code, and also run it on the cluster that we will create. So from now on, I will use the term node and GPU interchangeably. If a cluster is made up of two computers and each computer has two GPUs, then in total we will have 4 nodes or 4 GPUs. Distributed data parallel works in the following way. So at the beginning of the training, the model's weights are initialized on one node, so on one GPU, and then sent to all the other nodes using an operation called broadcast. Each node then trains the same model, because it started from the same initial weights, on a subset of the data. So maybe this one is, maybe one GPU is training it on the batch number 1, the second one is on the batch number 2, the third one on the batch number 3, etc., such that there is no overlap between this data. And every few batches that these nodes get trained this model, the gradients of each node are accumulated, so summed up into one node, and then the sum is sent back to all the other nodes. This operation is known as all reduce. Then each node updates the parameters of its local model using the gradient received by the previous step. So the gradient received by the previous step is the sum of the gradients of all nodes, using also its own optimizer, so doing optimizer.step. And then we start again from the step number 2. So we train it for a few batches, we have some local gradient, we send our local gradient to a central node, which will sum it up, and then send it back to all the nodes. Then all the nodes will update their parameters using this accumulated gradient, and then we continue again. Let's see all these steps one by one in detail. So step number 1. Our model's weight are initialized on one GPU. So imagine we have a setup with 4 GPUs. We have one GPU that will initialize the weight and send it to all the others. So now the value of the parameters, this is the value of the parameter, and this is the gradient. So the value of the parameter, imagine, is 0.1. We only have one parameter, so for simplicity. The initial weights are sent to all the other nodes. So now all the nodes have the same weights. So all the nodes now have the same parameters, all the same value. The next thing we do is each node runs a forward and backward step on one or more batch of data. This will result in a local gradient being calculated, because as we saw before, when we run loss.backward, we have a gradient being calculated of the loss function with respect to each parameter. This local gradient, of course, may be different for each node, because each one is training on a different subset of the data. And this local gradient may also be the accumulation of one or more batch. So it's imagine this GPU is training on each GPU is training on 3 batch. So we can accumulate the gradient for 3 batch, and of course, because we are training on a different subset of the data, this cumulative gradient, but still local, is different for each node. The next thing we do is we send all this gradient to every node sends its gradient to one single node, and this node will calculate the sum of all the gradient it receives. So imagine all the nodes decide to send their own gradient to the first GPU, and the sum is calculated on the first GPU. Then this operation is known as reduce, and later we will see how it works. Then the GPU that calculated the sum of all the gradients will send it back to all the other nodes in an operation that is known as broadcast. And the sequence of reduce and broadcast, because here I show it as a separate operation, usually is implemented as a single operation known as all reduce. And later we will see in detail how it works. But this is the key idea. So we have the model's weights that are initialized on a model. They are sent back to all the other models. So now all the other GPUs, they have the same weights, initial weights. They train it on a different subset of the data, so each one has a local gradient. They send each one its own local gradient to one node, which will calculate the sum of all these gradients and send it back to all the other nodes. So now they have all the same sum. Then they run optimization steps to update the weights using the same sum, so they will produce the resulting weights of the models will be the same for all of them, as you can see here. So now each node will update the value of their own parameters using the same sum of the gradient you can see here. So it's 0.3. They use 0.3 to update the value of their local parameters, and they will end up with the same weights. So each node updates the parameter of its local model using the gradient received. After the updates, the gradients are reset to 0, and then we can start with another loop. Now let's talk about collective communication primitives. So the operation that I showed before. In distributed computing environments, a node may need to communicate with other nodes. If the communication pattern is similar to a client and a server, then we talk about point-to-point communication, because we have one client connects to one server in a request-response chains of events. However, there are cases in which one node needs to communicate to multiple receivers at once. For example, in the broadcast scenario, right? We have one node that needs to send its weights to all the other nodes. This is the typical case of data parallel training in deep learning. So one node needs to send its initial weights to all the other nodes. Moreover, all the other nodes need to send their gradient to one single node to receive the cumulative gradient back. So collective communication allows to model the communication pattern between group of nodes. Let's visualize the difference between these two modes of communication. Imagine you need to send a file to 7 friends. With point-to-point communication, you would send the file iteratively to each of your friends one by one. Suppose the internet speed that you have is 1 megabyte per second and the file is 5 megabyte in size. What you do is first you send imagine you are here, so you have the file and you send it to your first friend, and it will take 5 seconds because you are sending 5 megabyte with a speed of 1 megabyte per second. Then you send it to the second friend, the third, the fourth, the fifth, the sixth, and the seventh. In total, the time to send the file to 7 friends will be 35 seconds. Of course, you may say, okay, but why not send the file simultaneously to all the 7 friends at the same time? Of course, you can do it, but the problem is your internet speed is still 1 megabyte per second. And the internet speed of sending the file simultaneously to 7 friends will be split among these 7 friends. So each friend will be receiving the file at a speed of 143 kilobytes per second, more or less. So the total time is still 35 seconds to distribute your file to your 7 friends. Let's see if there is a better way. So with collective communication, we introduce the first operator is known as broadcast. So the operation of sending a data to all the other nodes is known as the broadcast operator. Collective communication libraries like NCCL, which is pronounced Nickel, which is a library from NVIDIA, assigns a unique ID to each node, and this unique ID is known as rank. Suppose you want to send 5 megabyte with an internet speed of 1 megabyte per second, and let's see how the collective communication would work in the case of this broadcast operation. The first thing you do is you are here, so you have the file, you send it not to this friend here, but to the rank number 4. At the next step, we realize that the rank 0 and the rank 4 have the file, so they can send simultaneously to another friend. So rank 0 now will send it to rank 2, and rank 4 will send it to rank 6. But now we realize that rank 0, rank 2, rank 4, and rank 6 all have the file, so they can simultaneously send to it another friend. So in total, it will take 15 seconds to distribute your initial file to all the 7 friends, compared to the 35 seconds with the point-to-point communication. This approach is known as divide and conquer. With collective communication, we exploit the interconnectivity between nodes to avoid idle times and reduce the total communication time. This is how also your GPU sends the initial weight to all the other nodes. It's not one by one, because that would be too slow. It's not even in parallel, because anyway the connection speed is always the same. It would be split among all the receivers. What we do is we do this divide and conquer approach. So our initial weights are sent using this broadcast operation in this manner here, which is much faster. Let's see the reduce operation. What is the reduce operation? Reduce operation means that we apply it during the training when we want to calculate the sum of the gradient of all the nodes. So each node has a local gradient, which was calculated using a subset of the data, but they are all different from each other. And what we want is to calculate the sum of all these gradients into one single node. Let's see how it works. So the broadcast operator is used to send the initial weights to all the other nodes when we start the training loop. At every few batches of data being processed by each node, the gradients of all the nodes needs to be sent to one node and accumulated, so summed up. This operation is known as reduce. Let's see how it works. So imagine initially each node has its own gradient because they are training on a subset of the data, and these gradients is all different from each other. What we can do is each node will send the gradient to his adjacent node. And the adjacent node will sum it up with his own gradient. So the node 7, for example, will send his gradient to node number 6, and the node number 6, the receiver node, will be responsible for calculating the sum. And the same with the rank number 5 and 4 and 3 and 2 and 1 and 0. The next step, we have the sum here at rank number 4, rank number 2, and rank number 0. What we do is we send the sum here from rank number 6 to rank number 4, which will calculate the sum of the sum, and then also from rank number 2 to rank number 0. The rank number 0 will calculate the sum of the sum. And then we do a final step in which we send the sum that was present at rank number 4 to the rank number 0, and this sum here is the sum of all the gradients of all nodes. And in total, it took us only 3 steps to do it. So with only 3 steps, we accumulated the gradient of all nodes into one single node, and it can be proven that the communication time is logarithmic with respect to the number of nodes. And this is very typical of all the divide and conquer approaches. The all reduce operation, so what we saw before is that we are first broadcasting our data, so our initial weights, then we are reducing the local gradients, and then we need to send it back. The sequence of reduce and broadcast is known as all reduce, and is usually implemented as a single operation, which is faster than doing the sequence of the 2 operations. I will not show the algorithm behind all reduce, but you can think of it as logically as a sequence of reduce and broadcast operation. But remember that in practice, it's implemented as a single operation, and it's much faster than doing the 2 operations alone. Now, imagine you are training your model on multiple GPUs, and one node crashes. So imagine you are training in a distributed scenario like the one shown below, and suddenly one node is crashed. And in this case, 2 GPUs out of 4 become unavailable. How should the system react? Well, one way would be to restart the entire cluster, and that's easy. However, by restarting the cluster, the training would restart also from 0, because as you remember, we start from initial weights that are randomly chosen by one node, which are then sent to all the other nodes. But this would mean that we would lose all the parameters and computation that we have done so far when this node crashed. A better approach is to use checkpointing. So checkpointing means that we save the weights of a model on a shared disk every few iterations, for example, every epoch, and then we resume the training from the last checkpoint in case there is a crash. So remember the step in which we initialize the weights of the model in one node and then send it to all the others? Well, instead of just initializing it randomly, we just can initialize the weights of the model using the latest checkpoint available so that the training can continue from there. We need a shared storage for saving the checkpoints because it's PyTorch that will decide which node will initialize the weights. And so every node should have access to this shared storage. Plus, it is good rule in distributed system to not have one node that is more important than the others, because any node can fail at any time. So we should not make any assumption on which is the node that will initialize the weights. PyTorch will choose it. And actually, usually PyTorch chooses the rank number 0. But we should not make assumption on which node will be the rank number 0. So all nodes should be treated equally, so they should run the same code and they should have access to the same shared storage. And who, however, when we have a shared storage, who should be responsible for saving the checkpoint? Because if we make a code in which everyone is writing the checkpoint, they may end up overwriting each other. So what we do is, because PyTorch will tell us what is the rank of the current node, we will write the code in such a way that we check the rank of the current node, and if it's the rank number 0, then we save the checkpoint. If it's rank number 1, 2, or 3, we don't do anything. So it means that only one rank will be responsible for saving the checkpoint. But later, when we restart the training, we don't make any assumption on who will become the rank number 0. And as the PyTorch documentation says, it says that the rank is not stable. It means that if you restart the training, the rank number 0 may be assigned to another node. Okay. Now that we have seen how distributed training works at the theoretical level, so we accumulate the gradient that is calculated locally by multiple nodes and then send it to one single node, which then calculates the sum and send it back to all the others, which then update the parameter using this sum of the gradients, it's time to actually look at the practical training. So we will first build the infrastructure that is needed to run our training, and then I will also show you what are the code changes that we need to make to our existing training loop to make it distributed and run it on the infrastructure that we are going to create. I will use Paperspace as a cloud service, mostly because it's easy to use and doesn't require much setup time, even for beginners. I chose it over AWS because AWS has a lot of other setup that you need to do in order to even do simple operations, and it's easy to get lost. So I'm using Paperspace mostly for this reason, so that anyone with any kind of level of knowledge can do the same, can follow the tutorial very easily. So let's get started. Okay. The first thing we need to do is to go to my repository called PyTorch Transformer Distributed, in which you will find the code of the distributed model that we will be running on this cluster, and also the instruction on how to create this cluster on Paperspace. So I have already accessed my account on Paperspace. The first thing you will want to do is to create your SSH key, just like you do on GitHub, so that you can use this your public SSH key you need to associate your public SSH key to your account here so that you can connect to the machines that are created on Paperspace. Okay, the first thing we need to do is to create a private network on which we will connect all these two machines. So we will create two machines that are connected in this private network, and also a shared disk that can be accessed by both machines. We will use a machine that has 2 GPUs, so in total we will have 4 GPUs on which we will run the training. So let's create our private network. Networks here, and we create a new network. Remember to choose the same region for your computers and the cluster, and we will call it distributed training. Okay, now we have our subnet, you can see here. The next step to do is to create two nodes of type of, we can choose any node actually. I chose this one because I wanted to test two machines, each one having 2 GPUs. And we use ML in a box as the operating system, so as the image of these machines. So we create a new machine, ML in a box. The machine we will do is multi-GPU, P4000 multiplied by 2, this one. The region is the same as the network, so New York 2. The disk size 50 GB is enough. In total, I think last time I created this cluster and I ran it for many epochs I spent $5. So I think you should not spend more than $5 for running your own distributed training. It should not be more expensive than $5. The first machine, we will call it CUDA 0. The network, we need to select the network that we have created before, and we choose public IP dynamic because otherwise we cannot connect to the machine without a public IP. Then we never create a snapshot because we don't care about backup for now. And the price of running each machine should be around $1, you can see here. So we created the first machine. And then we create also the second one. So ML in a box. The machine is this one. New York, disk size. This one we will call it CUDA 1. Distributed training, dynamic. We don't save and create machine. Last but not least, we need to create a network drive of 250 gigabytes. We can create, this is the smallest one they have available, so that's why I chose 250 gigabytes. We will call it model training. 250, New York, and distributed training. They must belong to the same network as the two machines. Okay, create. Okay. So they are provisioning and starting the two machines. Now we will configure the machines. So we need to install some packages. First of all, we will need to install ifconfig because we need to have the IP address. And while installing ifconfig, I ran into an error with a seahorse, and I show also how to solve this error. We will then mount the network drive, and then we will clone this repository, install all the packages that we need for running this code, and then we I also recommend using weights and biases for keeping track of the loss, etc., of all the metrics that you need during the training of this model. So I recommend you register on weights and biases, and then you install it and use it also for this code, for running this code, because it will make it easy for you to visualize the training metrics. Okay, the CUDA 0 is ready. We can see some information here and connect. This will give us the IP address. We connect to it. Yes. Wonderful. So now we are inside the machine. The first thing we do is we update all the packages. Okay. We do also install the net tools, but I remember it will run into an error. But looks like this time it doesn't, which is good. Let's try ifconfig. Wonderful. So now we have the IP address of the first machine, which is this one. This is the private address that belongs to your subnet that you created here. So the one you created here, 81.0. Okay, now we can do we need to keep track of this IP address because later we need to modify the host, and this is actually needed because I ran into an error with the PyTorch when running the distributed training because it could not reach the other node. So I had to modify the host by mapping the host name of the other nodes into its IP. Okay, let's mount the network drive following just the instructions I have written. So we install this package. Let me call this one CUDA 0. Okay. Then we created the directory in which we want to mount this network drive. And then we have to run this command here. You can see it here. But we need to replace the IP address and the username and password of the drive. So let's first paste it. Then we need to replace this one with the IP address and the network share name, which I show you how to find. We go here, drives, and we can see here the address. So we do, but we need to replace the escape character with the // Okay. And the network drive username is this one. Let's run this command. The password is also here. We can copy it. Voila. Now it should be mounted. The first thing we do is we clone our repository. So we are in the home directory of the default user, so Paperspace. We can clone it directly here, no problem. We then cd, and then we install the requirements. Okay, now we have installed the requirements, so now we can log in into weights and biases using this command here. But remember to copy the key from the website of weights and biases, so which can be found here. Let's run. And should be okay. Okay, now we are ready to run the training command on the first computer, but we need to also prepare the second one. So let me prepare the second one. Of course, in a real scenario, you would create a Docker file and you would run everything using Kubernetes, so it should be done automatically. But in this case, because most of you maybe are not familiar with Kubernetes or Docker, or you just want to run very fast your training to see how it works, so I recommend using Paperspace because it's very easy to configure all the setup. Just like before. Okay, now we also clone here. So we clone the same repository on both computers and then we run the same code for training, but we will see later how to do it. Okay, now we do login with weights and biases. And now we are ready to run the training on both computers. Okay, the command that you need to run in order to run the training on both machines is the same, but we first need to take the IP address of the computer that we will choose. So one of the two computers will become the rendezvous master. It means that all the communication will be managed by that node and all the others will adapt. Now, of course, to make it more fail-safe, we need to create, we can use, for example, a dynamic IP that can be mapped to another machine in case the master crashes, so that we can restart the training using always the same IP. But in this simple case, I will configure it by hand, otherwise I need an orchestration tool and that will complicate all the scenario. So in this case, I just want to show you how to do distributed training. I don't want to spend too much time creating the perfect infrastructure, which you would ideally do in a real scenario. So we take this command here, and as you can see in this command, we need to tell the IP address of the master node here. So which one we will choose the master? In my case, I will choose CUDA 0, so the first machine I had created, and the other one will be kind of the slave, even if they both perform the same operation. So we find the IP of this slave here, which is this one, and we put it in the host file of the master. And also I need the host name of the slave, which is this one. Perfect. So okay, so we need to paste here the IP address of this node and also its host name, which is this one, and that's pretty much it. Now we can start the training. So we take the IP address of the master now. So CUDA 0 is our master, which is this one, and we put it in the command in this position here, and we cd to the torch, and we can run the command. So in this command, what we are saying is TorchRun is the special command that will create the cluster and will manage all the cluster creation and communication. It will run our training loop. You can see here. First of all, we need to tell how many processes we have in this cluster. So we have 2 computers, and how many processes we want to create for each node. So how many GPUs we have for each computer. So this is the number of GPUs per computer, and this is the number of computers. So we have 2 and 2. This is a unique ID that indicates this particular cluster. It should be unique for each cluster. And this is the backend library that is managing the communication for us. All the parameters after the file name that we will use for training are the arguments that are passed to this file here. So in our case, we are running with a batch size of 8. We are also telling him that the model folder, so where the checkpoints should be saved, this is the shared folder that we created before. So the mount file of the shared network drive. We run the same command on both computers, and this will start the training. So we do it this one. And also on the other one. As you can see, this computer here is not proceeding. It's waiting for the other. So now we run also it here. And now it should proceed. Yeah. So now both are proceeding. Oops, I forgot to set the host file on this computer here. So I retrieve the IP of this one. So IP of this one, and also the host name of this one, and we put in the host file of the other computer. So okay, let's run again the training. Looks like it's proceeding, so they are both doing, yeah. They are both building the dataset, now the tokenizer. So if you have watched my previous video on how to code a transformer model from zero, this is exactly the same code, except that I have added some things to manage the distributed training, but it's very minimal code change, and later I will show you step by step how I done. So as you can see now, the training is running in parallel. The first thing you will notice is that the weights and biases is only initialized on one node, because we cannot send the metrics from multiple nodes because it will interfere with each other. So we send the metrics only from one node, and it's the node with rank number 0. We will see later how we check this information. As you can see, they are both training on a subset of the data. So this one is training on 910 batch, and this one also 910 batch. It means that in total we have 1,820 batches in total. And each one is calculating a local gradient and sending it to the other, who will calculate the sum of this gradient. Actually, we have 4 nodes here because we have 4 GPUs. So each GPU is calculating a local gradient, and each gradient is sent to the rank number 0, which will calculate the sum of all these gradients using the reduce operation, actually the all reduce operation, because then it will send back the sum to all the other nodes, who will then update the parameters using the sum of these gradients that it has received. Another thing I made a mistake is that this 910 is not multiplied by 2, because it's not the rank 2 is actually, later we will see what is the difference between local rank and the global rank. But we have 4 nodes. Each node is working on 910 batches of data. So I only show one because TQDM will otherwise, if I show the TQDM for both GPUs, it will interfere with each other, this progress bar basically here. So I only show one progress bar per computer, not 2, because each computer has 2 GPUs. So actually I should have 2 progress bar, but I only show one, otherwise the visualization is very bad. So first of all, let's navigate the code to understand how it works. Let me open the project. Okay, let's see here. Let's start from the train file. Okay, the main difference that we have compared to the original code that I built in my previous video, but it's the same. This code, these changes that I'm showing here will apply to any training loop that you have built. So it's not only for this one, this particular code. This will apply to anyone. Okay, the first thing we do is we read these two variables that are, so when we run the code with the TorchRun, TorchRun will insert some environment variables into our environment that we can read. One is called rank and one is called local rank. Let's see the difference. Okay. The local rank basically indicates the number of the GPU in the local computer, while the global rank, or also called just rank, indicates the number unique ID of the GPU among all the cluster. So if we have 4 GPUs, the rank will be unique among all the cluster, while the local rank is not unique, but it's unique to the local computer. The local rank is useful, for example, when we want to print, for example, only on 1 GPU per each computer, while the global rank is useful when we want to only one GPU to perform an operation among all the others. For example, if we want to initialize weights and biases or any other service that should be initialized only from one node in all the cluster, then we use the global rank, which is this environment variable here. While if we want to use something, for example, for printing, or only one local GPU should use the TQDM or the progress bar or any other stuff that can interfere with each other on the local computer, then we use the local rank. So the first thing I do is I load these two environment variables and save it into the configuration. The second thing I do, okay, I print the configuration. The first thing we need to do to initialize the cluster, and this is where the TorchRun will stop waiting for all the nodes to connect, is to call this function here, init process group. This init process group belongs to a package that I imported here called torch.distributed. So these are the imports that we need to make in order to use distributed training. So torch.utils.data distributed, we need this distributed sampler, this distributed data parallel, this init process group, and destroy process group. So this is the first thing we do. So we read the environment variables, we save it somewhere so we can access the local and the global rank. We call this function here, indicating the backend that we want to use. I am using CUDA, so I want to use Nickel, so which is NCCL. We can also use the local rank to tell CUDA which is the GPU we will be doing training upon. So each computer will have each GPU will be given its local rank with relative to the current computer. So the first GPU will be assigned local rank 0 and the second GPU will be assigned local rank 1 on each computer. So we set here. Then we run the training loop, and after the training loop has finished, we do destroy process group. Let's see the detail of this training group. So when we do the training loop, first of all, here I disable the training on the CPU because we are using distributed data parallel, so it only works with the backend Nickel, it only works with CUDA. So I'm disabling on the CPU. The second thing we do is when we create the data loader, so here, so the train data loader and the validation data loader, we need to disable the shuffling on the data loader and introduce this parameter sampler, and we need to pass an instance of the distributed sampler here in which we tell him what is the data set and we want to shuffle it. So we shuffle it using distributed sampler, not the data loader here. And the next thing we do is we create the logic for preloading the checkpoint. So we check if we want to preload the checkpoint. In my case, the default configuration says that we should always load the latest checkpoint. You can see it here. So the default configuration says that we should load the pre-trained, the latest checkpoint available. So the latest checkpoint file is retrieved using the path that we passed using the command. So remember here we have a path that indicates what is the directory where we save the checkpoints, and we use this one. If there is a latest checkpoint, this will be loaded in our model. So our model is created here. So we create an instance of our model, which is just basically where you get the instance of your model, and then you can preload some the state dict here, and also the optimizer state dict and all the other global variables that should be preloaded for resume the training. If the global rank is 0, we also initialize the services like weights and bias. In the case of weights and bias, we also may want to resume the training from the same run in which we last crashed. So every time we save the checkpoint, we save also the run ID of the weights and bias run, and we can restore it if we restore the checkpoint. The big part that introduces the distributed parallel training is this. So now we have our model, which could be anything. In the case of my code, is the transformer model. So it's a special class that I created in my previous video. This one here, it's just the nn.model, this one here. We need to wrap it in an instance of distributed data model. You can see here, and we also indicate what is the device ID we will be using. So the GPU ID, which is the local rank. We also, with the global rank 0, we can also initialize other stuff. In this case, is just weights and bias. The training loop is the same as the non-parallel code, except that instead of running directly the model, so if we before do model.forward, we need to do model.module.forward. So if we need to access the encode method of our model, which is, for example, this method here, we cannot access model.encode. We need to access model.module.encode because this model refers to an instance of distributed data parallel. If we want to retrieve the original model, we need to do model.module. And every time we run loss.backward on this module, PyTorch will intercept this and will calculate the gradient, the local gradient. And after it has calculated the local gradient, it will send it to all the other nodes for accumulation and then receive back the accumulated gradient. And then this cumulative gradient is used when we use optimizer.step. And then optimizer.0 will set it to reset it to 0. When we want to save the checkpoint, which for example we can do every epoch, in my case I do it every epoch, I save it only on the global rank number 0 because I don't want to save the checkpoint on all the nodes, otherwise they will be overwriting each other's checkpoint. So I only do it on the global rank 0, as you can see it here. And this is pretty much what we need to do. Let me show you a template that you can follow for your future projects on how to integrate the distributed data parallel in your existing code. So let's see. Okay. This is a template that you should follow for your future projects. The first thing you do is you read these two environment variables called the local rank and rank. The first one indicates the local rank, so the number we saw before, so the number of the GPU relative to the local computer, not to the entire cluster. The second one indicates the global rank, which is a unique identifier for this particular GPU among all the GPUs of the cluster. We then call the function init process group. We indicated the backend we want to use for, in case of CUDA, which I think is most of the cases, is Nickel because it's the best one. And it's made by NVIDIA. So the second thing we do is we set which device CUDA should use, which is the local rank. Then we run the training loop. The training loop, only on the global rank number 0, we initialize the services like weights and biases. We create our data loader by telling him that as a sampler it should use the distributed sampler here and using shuffle, but not shuffle here on the data loader. We create an instance of our model, which is our custom class indicating our model. And if there is a latest checkpoint, we can load it now. After we have loaded the latest checkpoint, we need to wrap our model into an instance of distributed data parallel by also indicating the device ID it should use, which is the local rank. All the rest is the same, except that on the global rank number 0, we can collect some statistics. So for example, we can send some statistics to weights and biases. And only on the global rank number 0, we save the state of the model every epoch, for example, so that if the training crashes, we can resume from the latest checkpoint. Let's try to simulate a crash. So let's go here. Let's see how is the training going. So as you can see now, we are already training on the epoch number 1, so one epoch is already done. And our code should be in such a way that, as you can see, the code I built here, we are running validation only on the global rank number 0. Actually, you don't have to run validation during this distributed training, you can do it asynchronously, creating another, for example, node that reads the latest checkpoint and runs the validation asynchronously, so that our GPU can work directly always on the training and not wasting time for validation. Because otherwise all the nodes are waiting for the node number 0 to run validation, and this can be expensive for bigger models. So we can do it asynchronously. Okay, now we can see that the node number 0, all the nodes are training the epoch number 1, as you can see here. So I will try to simulate a crash and see that the distributed training will resume from the checkpoint of the epoch number 0 that we have already completed. So let's make it crash. I will crash the master node directly, so we can try the worst case scenario. This one has crashed, so I just killed the node, and we see that this one should also be killed after a while. Okay, this one is also killed. We can restart using the same command as before. As you can see, they are loading the dataset, loading the tokenizer, and preloading the model, as you can see here. The model that was previously saved by the global rank number 0, so now they should resume the training from the first epoch, not from the 0th epoch. And yes, they are starting from the epoch number 01, so because the epoch number 00 has already been done. And this is how failover works. So you basically save a checkpoint every once in a while, then you can restart the training from that checkpoint. When you save a checkpoint, you should also save all the variables that are relevant to resuming the training. So if you have some state variables, like for example, a global step counter, or you have some other counters that you need to keep track of, you can save them in the checkpoint and then restore them when you load the checkpoint. Okay, let's stop the training here. You can try to experiment with yourself with the Paperspace. I think it's quite easy, and let me know if you have any problem. I will try to help you. Okay, now let's look at how distributed parallel training, so distributed data parallel, was integrated into PyTorch. So because there are some clever design choices into this to make it very fast. Let's review them. So first of all, when does PyTorch synchronize the gradients? Well, this happens when we call loss.backward, because when we call loss.backward, this will lead to each node calculating its local gradient, which is the derivative of the loss function with respect to each node in the computation graph. And each node will send its local gradient to a central node, which is the global rank number 0, and receives back the cumulative gradient through an operation that is all reduce. Each node will then update its weights, so the parameters of the model, using the cumulative gradient and, of course, the learning rate of the local optimizer. We can avoid PyTorch synchronizing the gradient at every backward step and instead let it accumulate it for a few steps, for example, for a few batches, using the no-sync context. Let's see how to integrate it. So usually, you run the forward and the forward step, then you run the backward step. This will lead to synchronization. Then you do optimizer.step and then optimizer.zeroGrad. However, if we want to do it every few epochs, we don't want to run the synchronization at every step, we can use the no-sync context you can see here, which is a method provided by DistributedDataParallel, which is the wrapper of our model. And basically we create this context manager. We run the forward step and the backward step, and we don't call optimizer.step. When we are outside of this context, we still need to do the forward and the backward step. Then we can run optimizer.step and zeroGrad. Basically, this no-sync will disable the synchronization of the gradient, but it will let it accumulate locally for a while, and after a while we can synchronize. Also, there is another very clever trick in PyTorch, which is the computation-communication overlap. So since each GPU needs to send its gradient to a central node for accumulation, this can lead to an idle time in which the GPUs are not working because they're communicating, right? So each GPU will perform the forward step, then it will perform the backward step, and then there is some communication overhead because then GPUs need to synchronize the gradients with each other, calculate the cumulative on one node, and receive back the cumulative one. If we do this operation sequentially, it will lead to a big delay in the GPU because this time they could do some other meaningful work for the training. While so what PyTorch does, it will overlap the communication while running the backward step. Let's see how it works. So as you remember, we have a computation graph, right? So PyTorch will communicate the gradient of a node as soon as it is available, because as you remember, we calculate the gradient of the loss function with respect to each weight. But to calculate the gradient of the loss function with respect to each weight, we need to calculate the gradient of the loss function with respect to the intermediate nodes. So for example, first we compute the gradient of the loss function with respect to the output, then we compute it of the loss function with respect to the layer, the weights of this layer here, which are the weights and the bias. But these are already available, so we can already send them to the other nodes and get back the cumulative one. So this can already be done as an all reduce operation. Then PyTorch will calculate the next layer, and this one, since it's already available, we can already send it to the other nodes and receive back the cumulative one, etc, etc, etc. So while PyTorch is computing the backward step, we can already communicate to the other nodes the gradient of that we have already computed and receive back the cumulative one. This will result in a very fast speed up. And to make the communication even faster, instead of sending one gradient at a time, PyTorch basically will create buckets of gradients. So every time a bucket is available, it sends it to the other node and receives back the cumulative gradient for that bucket. Then after the second bucket is available, it will send the second bucket and receive back the cumulative. After the last bucket is available, it will send it to the other nodes and receive back. This way, we can, as you saw before, we can overlap the communication overhead with the calculation of the backward step. So while we are calculating the gradients, we already send them, so that the total time to process the forward, the backward, the communication, and the updating, it's less because two steps are overlapped with each other. PyTorch recommends 25 megabyte as the size of the bucket because we don't want it to be too small, because the overhead of the communication of each bucket would be too big. So we have a lot of overhead for each bucket, so we can spread this overhead on bigger buckets, so less in number but bigger. But we also don't want it to be too big, because otherwise we are not using the communication channel while we are computing the gradient. So thank you guys for watching my video. I hope you learned a lot. In this video I introduced the data parallel training, and I show you how to create the infrastructure and also how to run this code of distributed training on the infrastructure that we have created. I also show you how PyTorch works under the hood, so that you can understand how the gradients is synchronized, and also at a mathematical level, how does it work. Please like and subscribe my video if you liked it and it was helpful for you. I also recommend watching my other videos, because every time I make long videos in which I give a lot of knowledge. And let me know if there is something you don't understand. I will try to help all of you. Thank you guys.